Okay, so let's look a little bit more generally at finding gradients using the limit theory. So if we wanted to take what we just did and generalize it a little bit more, let's start out with the same points. We're going to use point F is 0.11, and that means that point M is then going to be generalizing 1 plus h, whatever that is, and then our y value is going to be the function of 1 plus h. So there's our two values. So now we're going to use our slope formula. We're going to plug that in. So we end up with a function of, or f of 1 plus h minus f of 1. Excuse me, I didn't put this in up here. So our x value is going to be f of 1. There we go. Okay, that's much better. Okay, so now let's put this in. And then we're going to have 1 plus h minus h. And you can see where we got those. So these two are together, and these two are together. And then we also have these and these. This is where we got them. And all this is, again, it's just y2 minus. So if you forget it, that's okay. You should be able to kind of reason this out using the slope formula. Okay. And so from here then, we can take this and we can simplify a little bit. And these h's will cancel out. And so we're left with f of 1 plus h minus f of 1 over just h. Now, more generally, we could take this and we could write, instead of, now we're not using a specific function at this point, like before we used the parent function of a quadratic. So let's just say instead of using this, now we're just using in general, it could be whatever function you want to plug in, f of x. So let's look at what this would look like. Here it is, the limit as h approaches 0 of f of a, whatever a is, and a is our point on the line, f of a plus whatever h is, minus f of a. And so all we did was, in place of f up here, now we're using a new f, and it's a generalized one where we say that this is a, and then this is f of a, which means then that our point M is going to be a plus h, and then it's going to be the function of a plus h. And that's really all we did. So it's it looks more complicated than it really is, and all of this is going to be over h because remember we were able to simplify back here, and so this is what we come up with as a very generalized form of this. Now let's look at an example here. So we want to do this one, f of x equals, now we're going to use the parent function again, and we're going to use, as our point f, we're going to use 2, 4. So that means then that a equals 2, and that f of a equals 4. So let's start plugging pieces in now. And we can find that the gradient of tangent at point F, let's write it out, the limit as h approaches 0 for f of 2 plus h, remember where we got that from, minus what? Minus our value, our y value for point F, which is function of 2. We already know that's 4, but that's fine. Now all of this is going to be over whatever h is. At this point we don't know, so we're just going to plug this in. And so now when we plug in f of 2 plus h, it's going to give us 2 plus h squared. And when we plug in 2 into our function, it's going to give us 4, which we already knew, over h. Now we can do some simplifying here, and we should find out that 2 plus h equals h squared plus 4h plus 4 minus 4. Those two will cancel. Over h. Factor out the h again, and we get h times h plus 4 over h. Cancel, and h plus 4 is it. So now we would write the limit as h approaches 0 of h plus 4 or 4 plus h, however you want to look at it. But remember, they can't be equal, so h cannot be equal to 0. But hypothetically, we're going to plug that in, and when we do, we find out that our gradient for the function at the point f, which is 0.24, our gradient is 4.